Hello everyone. Welcome to First Online University, a global platform for all your education and growth related needs. In this lecture, we are going to start with the details of alkanes. And in this particular lecture, we will be focusing on the nomenclature and conformations of alkanes. Before we begin, a piece of information for you. You can use the coupon codes Mission JEE or Mission NEET while you enroll at First Online University for Mission JEE or NEET. Let us now start with the IUPAC nomenclature of alkanes. Now, what do we mean when we say nomenclature? Nomenclature means how do we name any compound that comes in front of us. So when we are talking about alkenes, and we in particular are talking about the nomenclature of alkanes, it means we are discussing the rules for naming these molecules. So let us talk about the nomenclature in a very systematic manner so as to be able to remember this for a long term, because nomenclature forms the foundation of organic chemistry. And if you're not able to name any compound, or if given the name you're not able to predict what the compound is, then it becomes very difficult for you to proceed ahead with the question. Okay, so uh, depending upon the number of carbon atoms, we will be giving a root word and then the parent name, and then we'll see. So root word is basically, the root word is, okay, we'll see what it is. So root word plus 1 degree suffix. So what does this all of this mean? We'll understand it very quickly. And the structure, obviously. So if I say the number of carbon atoms is 1, the root word is meth. The parent name here in case of alkanes would be methane, and the structure is simply CH4. If the number of carbon atoms is 2, the root word would be eth. The parent name would be ethane, because we are talking about alkanes as of now. So ane is the suffix that is used. When I said 1 degree suffix means the suffix for alkanes. When I say 2 degree suffix means for alkenes. 3 degree suffix for alkynes. That would be ene for alkenes, ine for alkynes, ane for alkanes. Okay, so it comes from, so if you look at this word alkanes, this ane is where this and the rest of it will come from. Okay, the structure would simply be CH3, single bond CH3. If we have 3 carbon atoms, the root word is propane. The structure is this: CH3, CH2, CH3. If we have 4 carbon atoms, the root word would be but, the parent name would be butane, and the structure would be CH3, CH2, CH2, CH3. Then if we have 5 carbon atoms, the parent, okay, so for 4, we need not only have this CH3, CH2, CH2, CH3 as a non-branched or a straight chain, we can also have a branched chain. Then let us look at the rules of IUPAC nomenclature. And similarly, for 5 carbon atoms, we have pent. For 6, we have hex. For 7, we have sept. For 8, we have oct. For 9, we have non. For 10, we have dec. These are the root names. And ane will be added in the parent name because we are going to be talking about alkanes particularly. So now what are the rules for IUPAC nomenclature? All of these rules have to be followed in one particular order, and the first rule has to be followed first, then the second, then the third. Sometimes, some of the rules would have to be violated while naming any particular compound, because uh, something else would have been said in rule number 1. So maybe you will have to violate rule number 4. Not exactly violate, but you will have to number the compound according to rule number 1 and not rule number 4. So let us look at these rules, and it is very important that you remember these rules. Nobody is going to ask you to write down these rules. It is in your brain that you have to remember them, and then you will have to solve questions based on them. So let us look at the rules. The first one is you have to select the longest possible chain as the parent chain. Then you number the chain in such a manner that the substituents should get the lowest possible number. Okay, so the carbon that contains the substituents should be getting the lowest possible number. So supposedly we have a substituent on carbon number 4 from this end and on carbon number 2 from this end. So we'll start numbering from the end where the carbon containing the substituent gets number 2. You will have to separate two numbers. So while writing the name, if it's like we have methyl group on second and third position, so you will have to separate the numbers with commas. 2, 3 dimethyl and so on. Okay. Alphabet and number has to be separated by hyphen. So if there are two numbers, you will separate them with a comma. Then 2, 3 dimethyl. So 3 and D, they are number and alphabet, so they'll be separated with a hyphen. You have to write the name of the substituent in alphabetical order, irrespective of whether the substituent is at the second position or 10th position. While writing down the name, you will always start with the letter that comes first in the order, alphabetical order. If there is more than one similar substituent, apply the numerical prefix di, tri, tetra, and so on in order to indicate the number of similar substituents present. If an organic compound contains more than one longest carbon chain, then in that case, the chain which has more number of side chains, that is more branches, will be selected as the parent chain. Now let us solve a few examples to get acquainted with these rules. So let us write the name of the following compounds. Example number 1. Supposedly this compound is given to you. Now, first of all, you will identify. I'm just solving example 1 for you. Rest of the questions you can do yourself. I'll just give you the solution. So if you look at this question, you first identify the longest carbon chain, which clearly is this one along my arrow. Okay. So you identify that this is going to be the parent chain. Once you have identified the parent chain, the next thing is you have to start numbering. Now, whether to start numbering from left hand side or right hand side, that you will decide on the basis of the positions that these substituent containing carbons will get. So obviously when you start numbering from the left hand side, 1, 2, 3 and so on, so you will have the substituents at second and third position. So we will start numbering from here. So longest chain is hexane because it has 6 carbon atoms. Now the second thing is that you have to start numbering the chain and you will start from 1, 2, 3 and so on up to 6. So now you will have to name the substituents, and since we have to start writing the name with the substituents in the alphabetical order, out of methyl and ethyl substituents, ethyl, E comes before M in the alphabetical order. So the name is going to be 3-ethyl, 3-ethyl, 2-methyl, 2-methyl hexane. Okay. Example number 2. This is the structure. Now you solve this by yourself before I give you the solution. Write down the name of this compound and then check your answer when I give you the solution. Okay, so I hope you must have written the name by now. Let us see what its name is going to be. So when we start numbering, obviously we've identified that this linear chain is the parent chain. We've numbered it from 1, 2, 3 to, 1, 2, 3, 4, 5. And now we have to start naming the substituents. So it's going to be 2, 2, 4 trimethyl pentane. Now we move on to talking about conformations, and we are going to take the example of the simplest molecule containing 2 carbon atoms, simplest alkane. Obviously, methane is the simplest alkane, but when we are going to talk about, conformations, we require something more complex than methane, and then the simplest molecule that is left is ethane. So we will be talking about the conformations of ethane. So When I say conformations gives rise to rotamers. Now, what are rotamers? Rotamers are actually conformers which are capable of having a single rotation about a CC single bond. So, if we talk about conformation, so these isomers are formed by the rotation of CC sigma bonds. Alkanes can have infinite number of conformations because we can rotate them from 0 degree up to 180 degree. So 180 conformations already there. There can be a lot more. The rotation around a CC single bond is not completely free. There are going to be some hindrances. It is hindered by a small energy barrier of approximately 1 to 20 kilojoules per mole, and this is due to weak repulsive interactions between adjacent bonds. So when you have adjacent bonds, there are going to be some repulsive interactions that will hinder the rotation about this CC single bond. This repulsive interaction is what we call as torsional strain. Now, if we look at ethane as an example, ethane molecule contains a CC single bond with each carbon atom being attached to 3 hydrogen atoms. What do we do is we keep one carbon atom stationary and we try to rotate the other carbon atom around about this CC axis. This rotation results into an infinite number of conformations. However, there are two extreme cases. One conformation in which the hydrogen atoms that are attached to two carbon atoms are as close to each other as possible. We have already talked of this particular fact when we were talking about rotamers in the first few lectures of General Organic Chemistry, that is GOC, that is Basic Principles and Techniques in Organic Chemistry. So we have discussed that when the hydrogen atoms on the carbon atoms are present as close to each other as possible, the conformation is eclipsed conformation. And when they are as far apart from each other as possible, we call it as staggered conformation. Eclipsed and staggered conformations can be represented using sawhorse projections or Newman projections, right? Both of them. Now let us look at the sawhorse projections first. So when I look at this particular bench that has been shown, this is exactly what a sawhorse projection would look like in case of the eclipsed conformation. So in this projection, the molecules are viewed along the molecular axis. So this is my molecular axis, this. Okay? This is my molecular axis. Now, a long straight chain which is projected on the paper represents a CC bond. This represents a CC bond. The upper end of the line is tilted either towards, so this upper end is tilted towards right or left hand side. The front carbon is shown at the lower end of the line. This is the front carbon. And the rear carbon at the upper end. Okay, so it's like we are drawing a line like this. This is the lower carbon, that is the rear or the back carbon. This is how we are drawing. Okay, so a slanted line which is tilted either towards right or towards left. The front end is giving us the front carbon and the other end, that is the backward end, is going to represent the rear carbon. Okay, this is the front carbon, this is the rear carbon. This is how, see, this entire process is to explain how to draw the sawhorse projections. Now, each of this carbon has 3 lines attached to it that corresponds to 1 hydrogen each. Okay, and these 3 lines are inclined at an angle of 120 degrees. So if we look at these 3 lines, so in the sawhorse, you will have this line on the paper that is representing a carbon-carbon single bond. And each of these 3 lines have to be drawn in such a way that they are at 120 degrees to each other. So if you carefully see, this is somewhat a Y. Okay. This is one end, this is another end, and this is a Y. Y is this. Okay. So this is a Y and this is also a Y. Okay, so since the two Y's are facing each other like this, okay, this is going to be the eclipsed conformation. If I tilt, okay, so this Y remains like this. If I tilt this Y in a way that now the two lines of Y come here and the tail of Y goes here, then it is going to be the staggered conformation. So now you see, this is the straight Y, this is the inverted Y. Okay, this is going to be my staggered conformation. Now let us talk about Newmann's projections. The molecule is viewed at the carbon-carbon head-on. The carbon atom which is nearer to the eye is represented by a point, and the carbon atom that is far away, that is the rear carbon atom, is represented by a circle. We've already talked of this. This is just a repetition. The lines which are radiating from the center of the circle are going to denote the bonds of the carbon that is close to us, and the lines that are originating from the circumference of the circle are going to denote the bonds that are to the carbon atom farther away from us. Now, in case of staggered form, the distance between the hydrogen nuclei is 2.55 angstrom. And in the eclipsed form, the distance between the hydrogen nuclei is 2.29 angstrom, because in case of eclipsed form, the hydrogen atoms are as close to each other as possible, and therefore the distance is less. The dihedral angle in case of eclipsed form is 0. In case of staggered form, it is equal to 180 degrees. Now look at this Newman projection. This is the front carbon. This circle represents the backward carbon, the rear carbon in case of ethane. These are the bonds to the front carbon. And this, okay, look at this representation. This is exactly how you have to draw. Now, these red bonds arising from the circumference of the circle are representing the bonds on the rear carbon. This is the staggered conformation where the dihedral angle, that is the angle that this carbon, the next carbon, and the two hydrogens make with each other is 180 degree. Not these two hydrogens. It's basically the plane of this hydrogen, this carbon, and this hydrogen, this carbon, and this carbon. So hydrogen, back carbon, hydrogen, this carbon, and back carbon form one plane. Then this hydrogen, this carbon, and this carbon form another plane. And these two planes are 180 degree to each other. Therefore, the dihedral angle in case of staggered conformation is 180 degree. However, in case of eclipsed conformation, you have to draw exactly like this. Now here the dihedral angle is 0 degrees. So the remaining conformations in between these two extreme conformations, that is staggered and eclipsed, are called skew or gauche conformation. Make a note of the fact that apart from the eclipsed and staggered conformation, the remaining conformations are called skew conformations. Let us look at the relative stability. Obviously, the staggered conformation is going to be the most stable because the hydrogens or any other groups that are present or attached to the two carbon atoms are going to be at maximum distance from each other. So they are going to be highly stable because there is going to be no interactions, repulsive interactions between them. And also there will be no steric hindrance that will be provided from one or the other atoms to each other. Then comes the skew conformation, and eclipsed conformation is going to be the least stable. In eclipsed conformation, the bonds are very close to each other and therefore will have maximum repulsions. In staggered conformation, the bonds are at maximum distance and will have minimum repulsions. This is all about the nomenclature of alkanes and the conformations of ethane. You can subscribe to our YouTube channel for joining YouTube live classes for best NEET or JEE coaching. You can also download the First Online University mobile app for continuous learning through your smartphones. For such exciting educational experience, keep learning with First Online University.